All right, so let's go over this unit X sort of energy of reactions. So we have learned this already, but I just want to stress it again because it helps us understand acids and bases. All reactions require some activation energy. There's some energy required for any reaction to sort of get to the top of this hump and be able to get over the hump. And we call that activation energy. If it's small, then we say they're spontaneous. Exothermic is when the energy of the reactants is higher than the product, so that there's an overall downward trend in energy. So here's energy increasing as you go up. And as you can see, peroxide has more energy than the water and oxygen it creates. We call that difference in reactants and products the enthalpy, which is given delta H. And in this case, that would be negative because the enthalpy of peroxide is more than water and oxygen. So there's an overall downward trend. And in this case, that's minus 98 kilojoules. So the reactants are higher than products. In the reverse, therefore, it would be endothermic. So if we wanted to make water and oxygen become peroxide, because these chemicals are of lower energy than that, we have to overall put energy in. And thus, it would take 98 kilojoules to get up there, and there would be a larger activation energy than going from peroxide back to water and oxygen to get to this activated complex, this sort of midway point between these two chemicals. So it's not unlike how a bird sort of jumps from branches. If a bird's trying to go to a higher branch, it has to jump high, and then it sort of flutters down a little bit. And if the bird's already on a higher branch and going to a lower branch, it still hops up a little bit of activation energy to then go down to a lower point. So that's the same as what we're seeing here. The bird would have to jump up a little to go down, and if it was way down here, it would have to jump up a little more and then settle down a little bit. All right. So endothermic would be the opposite of what we just said. Here we have water and oxygen. It's trying to get up to peroxide. It turns out the enthalpy, the change in energy, is the same, but now it's positive because it's going upward as opposed to downward. There's still the same activated complex here in the middle where things are halfway in between. So endothermic reactions go up. They're going to have a positive enthalpy, which is delta H, and the products are going to be higher than the reactants. All right. So we can say that, so adding a catalyst will lower this energy. This activation energy goes down if we add a catalyst, and we did this in class. We added catalyst to the peroxide, and old foamy happened, and all sorts of foam created this water and oxygen. It'll increase the reaction rate because it doesn't take as much energy to get over the hump. It does not change, however, this enthalpy. It doesn't change the difference between the energies and the reactants and the products. It just changes the height of this activated complex. All right, so looking here, we did this, but since we're on a video, we might as well do it live. So here we go. So if I put some starting material here, and this were the activation energy, and I increase the activation energy. So as you can see here, the reactants have higher energy than the products. They're higher up than the products. So they're unable to get over this wall, and we can heat them up to get them over that wall. And at some point, one or two will get over that wall. There he goes. We got one over. All right. So once one's over, now it'll kind of stay over there. But what a catalyst will do is not change the height of this or that. What it will do is lower this wall and allow more things to get over by having a lower activation energy. So it's easier for things to get one way and the other. And this is what we call a reversible reaction. This is why I'm teaching this to you now, is because acids, specifically what makes a strong acid and a weak acid is this reversibility part. If it's sort of a 50-50 mix, then it's a weak acid. If, however, everything has a tendency to just go one direction, all right, so where we have just a whole bunch of these and very few of these, oops, wrong way. All right, so that would be a strong acid where you have a lot of the separated H from the A, and a weak acid would be more where everything's sort of 50-50, and so therefore the H is tied up with the anion a little bit more. So that's why I'm doing all that. But anyway, moving on. All right, so what is this activated complex we're talking about? This sort of thing at the height here of the energy. And that is a situation where the molecules involved have to be hitting in the right orientation and with the right amount of energy so that they can form the products or go back to the reactants. So here, if you see H2 and Cl2, it should make sense that each H has to hit that Cl perfectly so that each Cl can leave with an H. For example, if this were to hit in more of a long way where one H hits here and the other H is down there, that wouldn't be helpful for the activated complex because this chlorine would have no hydrogen. And therefore, that activated complex wouldn't work. So you want the proper position to react. And catalysts, what they can do, the reason they lower this activation energy is they can often orient these molecules so they're sitting correctly so that they can react in this way. And I think I've hit shoulders with someone in class to explain that. All right, the other thing you kind of briefly need to know is that because there's energy involved with reactions, if we doubled the amount of energy, or in this case, let's say we halved. So if we only used 1 mole of water instead of 2, and we wanted to get 1 mole of water instead of 2, we would get half the energy because 2 moles of water gives this much energy, 1 mole would give you half as much. And that shouldn't be rocket science, right? And in class, I lit 1 match and I lit 20 matches. And because I increased the chemicals of matches by 20-fold, I got 20-fold the energy, and it was much more light, right? Same is true with the reverse. If we want to do the reverse reaction, we're going to need more energy if we have more, or we're going to use half as much energy if we use less. Like if we use here 1 mole of hydrogen. So if we're going to do half as much, we only need half the energy here to do half the reaction. All right. I don't know if that made any sense, but whatever. Here we go. Nitroglycerin, we were talking about this with Bugs Bunny. Here's the balanced reaction. So Bugs Bunny, or Daffy Duck, puts nitroglycerin and gunpowder and a bunch of things in his stomach and he blows up. So the question is, where do you expect to find energy? Would that make energy a product or a reactant if Daffy Duck blows up when he drinks nitroglycerin? The answer is that would make it a product because he exploded upon drinking this stuff. So if 4 moles of nitroglycerin give 22,880 kilojoules, how much would 1 mole give you? And hopefully it makes sense that 1 mole would give you 1/4 the energy. So because 1 mole is 1/4 as much of this nitroglycerin, you'd get 1/4 as much of the energy. So it'd be 5720 kilojoules. All right, and if you drew the energy diagram, there would be a little activation energy and then a huge drop, and the difference in enthalpy between this and this would be that 22,880, because that's how much energy was released overall. So this activation energy you get back right here. So it's the difference then after that activation energy is recaptured that determines the enthalpy. All right, and that's all I'm going to do with that. So let's move on. I think I'm going to stop there. And that is that.